In this module, we'll learn about thermal analysis and the way of drawing cooling curves with the help of this thermal analysis. Okay, we'll move into the topic. Hope you all know what is a phase diagram. A phase diagram is a graphical representation of the physical states of a substance under different conditions of temperature, pressure, and concentration. And a phase diagram is plotted by taking 1 degree of freedom on the x-axis and other degree of freedom in the y-axis, or it's a plot of 1 degree of freedom against the other. And for constructing this phase diagram, it is necessary to determine the composition of the mixture at different temperatures, and this will be helpful in determining the equilibrium condition for solid liquid systems. This is done by thermal analysis. And thermal analysis is the study of the cooling curves of various compositions of a system during solidification. It is used for finding the shape of the freezing point curve for any system, especially those involving metals. And a plot of fall of temperature with time is called the cooling curve, and it's possible to determine the freezing point and eutectic point for any mixture of a definite composition from the cooling curves. Now, we look into the shape of the cooling curve for a pure substance. Okay, when a pure substance in the molten state is allowed to cool slowly and the temperature is noted at different intervals of time, a cooling curve of this pattern is obtained. Okay, initially at this point, let me take it as A. Okay, initially at this point A, the pure substance, that is 100% pure substance with no impurity in it, okay, that substance I have chosen, it's in the molten state during the initial point A. Okay, and it's allowed to cool slowly. Okay, now there is a drop in temperature, and the temperature and the rate of cooling, it's quite rapid. It falls along this line AB. Assume this is point B. Okay, it falls down along this line AB, and the fall of temperature is continuous. And when it reaches this point B, this is the point B. Okay, when it reaches this point B, which is known as the freezing point, the temperature becomes constant and it is indicated by a halt. See, you can notice this. It's indicated by a halt in the continuity of the cooling curve. Actually, at the freezing point, the solidification of this pure substance starts. Okay, we all know that solidification is an exothermic process, and hence the temperature remains constant at this freezing point TF. Since the heat evolved during solidification, it compensates for normal cooling, and the constancy of this temperature will extend till this point C is reached. Okay, or in other words, we can say that until the liquid is completely solidified. Then the fall in temperature will again continue from this point. Assume this is point C and this one is D. Okay, it will continue uh, rapidly. Okay, the fall in temperature will again continue as indicated by this part CD of the curve, which indicates that the hot solid that has been formed cools down slowly till its temperature becomes equal to room temperature. Hope you understand. The same thing, it's more clear in this diagram. Okay, so we have taken a pure substance, 100% pure substance. It's fused or it is melted and it's brought to its molten state, and then we are noting the drop in temperature with respect to time, and we are plotting a graph. Okay, these are known as cooling curves actually, and this is the cooling curve for a pure substance, pure metal. Okay, so initially the rate of cooling will be continuous. When the point B is reached, which is known as the freezing temperature, the solid substance begins to crystallize, and then the temperature remains constant till the point C is reached, that is till BC, the temperature remains constant, and after that there is a drop in temperature. That is, till BC the solid is getting crystallized, solid substance, assume it is some X, okay. It is getting crystallized from the solution, and this crystallization or solidification process continues till the point C is reached. When this point C is reached, there is again a drop in temperature, indicating the cooling process of this solid that is being formed during this solidification, okay. So this is the cooling curve for a pure substance, okay. Note the shape of the cooling curve: initial drop in rate of cooling, abrupt drop in rate of cooling, followed by a steadiness or constancy or a halt, and then again there is a drop in temperature. This is the case of a pure substance, okay. Cooling curve for a pure substance. Now we look into the cooling curve for a mixture of two substances, okay. Now we have taken two substances, assume it as X and Y, okay. Two solids, it's brought to its molten state. When a mixture of two solids in the molten state, I'll show the diagram and explain, okay. This thing, consider this thing. When a mixture of two solids in the molten state is allowed to cool slowly, okay, a continuous cooling curve is obtained initially, this AB. It's continuous, okay, and the change is abrupt. A continuous cooling curve is obtained initially. You can see from the graph that the rate of cooling along AB is quite rapid. This is when the separation of a solid has not yet commenced. We have taken two solids, right, X and Y, but in this portion, no solid separation has yet started. And at B, one of the solids begins to separate, either X or Y. Okay, one of the solid begins to separate at the point B. And as we all know, separation of a solid from the liquid solution is an exothermic process. And as a result of this, the rate of cooling is diminished as the separation of solid begins to commence. Notice this rate of cooling and this rate of cooling. Note the portion AB as well as BC. This rate of cooling is diminished when compared to this rate of cooling, okay. And that is, it's getting slowed down. You can see a distinct break at this point C, okay. There is a distinct break at this point C, which is the eutectic point, which shows that the eutectic point has reached, and the temperature remains constant along CD until solidification has completely taken place. In short, we can say that at A, both X and Y, both the substance are in molten state. It is allowed to cool slowly, and there is a rapid drop in temperature along the along the line AB. And at B, one of the solids begins to form, and thereafter the rate of cooling is not so abrupt, or it's getting slowed down. And at the point C, there is a sharp break, which indicates that the eutectic point is reached, or eutectic temperature is reached, and thereafter the temperature remains constant. At C, the second solid also begins to get crystallized or solidified, and along CD, separation of both X and Y occurs, okay. And at D, there is a complete separation of this mixture, okay, in solid form, and the temperature remains constant from C to D until solidification has completely taken place, and further cooling results in fall of temperature along DE. So we can notice three breaks in this cooling curve. One is at B, one is at C, and the other is at D. Okay. First one occurs at the freezing point of the mixture, where the first solid commences to solidify, and the second break occurs at the eutectic point, and the third one occurs when the mixture gets completely solidified. Okay, hope you have got some idea regarding this. Can you notice the difference between this one and this one. See, here there is a drop and constancy and again a drop. But here there is a drop followed by another drop and then constancy and followed by drop in rate of cooling. Can you understand? Okay. And this is the principle behind the method of thermal analysis, which is used for the study of solid liquid phase equilibria involving metals, and it is used to obtain the phase diagram for any two component system. Okay. Now we'll find out experimentally how to draw a phase diagram with the help of this cooling curve. Okay. Now prepare a mixture of two different metals, say X and Y. Here I have taken, and they have in this picture it's mentioned as A and B. Okay, we have taken two different metals A and B, and in this region it is 100% A, that is pure A, and in this region it is 100% B, that's pure B. And we are going to prepare mixtures of different composition, that is here it's 100% A. Also, what will be the middle composition? It will be around 50% A and 50% B. And in this region, it will be, which proportion will be higher? This A proportion will be higher and the composition of B will be less. Assume it is at this position, let's assume it is 90% A and 10% B. Similarly, if you move this side, the proportion of A will be getting decreased and the proportion of B will be getting increased. Okay. And can you understand? As we move towards the right side, the proportion of B is getting increased and the proportion of A is getting decreased and vice versa. Okay. Okay. Right. Now we'll see this. The same thing it's mentioned here. Okay. This point, let's assume. Okay. At this point, okay, around this area. At this point, it's written as 10% of B, right? When we consider this point, it's 10% of B and 90% of A. Slightly if you move this side, what will happen? It's around 80% of A and 20% of B. Okay, similarly, likewise they have drawn it. Now consider this point. What will happen? It's 90% B and 10% A. That's what it's mentioned here. Slightly if you come this side, it will be 80%, around 80% of B and 20% of A. Okay. Now we are going to prepare mixtures of these compositions. Okay, these compositions around 10 roughly. Okay, we are going to prepare mixtures of different compositions of A and B, and we are going to melt it. So melt it well, and so it will be going into the fused state or molten state, and then cool it. Cool the melt. Okay. When it is cooled, can you understand? So a number of mixtures of metals A and B of different compositions which are lying between 100% A and 100% B are prepared. Heat above their melting point. Now, in the molten state, naturally there will be only one phase, that is the liquid phase in each case. Cool the molten liquid slowly and record this fall in temperature with time. Okay, note it. In this way, we are getting different cooling curves. Can you understand? So, for example, this thing, let's assume this point. Okay, let it be around 10% B and 90% A. So initially the rate of cooling will be continuous till the point L is reached, and thereafter the rate of cooling will be diminished. It moves along the line Ls, and at L one of the solid is getting solidified, and when it reaches this point S, the formation of eutectic begins. Okay, thereafter it remains constant and again there is a drop in temperature. Right? Now this is the cooling curve for another composition. Say let it be for 20% of B and 80% of A. So initially the rate of cooling will be continuous, and when it reaches this point L dash, which is the freezing point corresponding to this mixture, one of the solid begins to separate, and thereafter the rate of cooling gets slowed down, and when it reaches this point S dash, formation of eutectic begin. It remains constant, and thereafter the rate of cooling continues. Can you understand? Likewise, we are drawing cooling curves for each and every composition of this system. Okay. So, in this way, we have obtained several cooling curves. The same thing it's mentioned here. Can you understand? So, rate of cooling will be continuous, and then, okay, rate of cooling, this thing, okay, rate of cooling, and then, sorry, okay, and then it's getting, actually it should be like this, it will be coming like this, and then this eutectic will be attained. Rate of cooling, and then when this point is reached, the solid begins to crystallize, and this corresponds to freezing point of the mixture. And then what will happen? Okay, then again there will be a break in this cooling curve, and then it will attain this eutectic composition. Like this, we are drawing the cooling curves of various composition. This diagram is more apt, I think so. See, this is the freezing point corresponding to this particular composition, assume. Okay, so I am drawing a phase diagram taking composition in the x-axis and this temperature in the y-axis. Okay, so this corresponds to the freezing point of mixture of particular composition. What is the particular composition? I have assumed it as around 10% B and 90% A. Can you understand? So this thing. Similarly, likewise, we are drawing the we are marking the freezing points corresponding to each mixture. Okay, we have drawn the same thing. When you recollect whatever I have told and grasp the ideas, you can interpret the meaning of this phase diagram. Okay, so this thing, this is the freezing point of sorry, this we'll see later. This is the freezing point of this mixture corresponding to 10% B and 90% A. This is for 20% B and 80% A, and this one for here 40% B and 60% A. This one 50% B and 50% A, so on. Okay, so they're connecting the freezing point. See, this one, this one, this one, this one. That's what we have drawn here. Okay, freezing points are drawn. Okay, see, you can see from these cooling curves that the first break in each curve occurs at the freezing point where the separation of one of the solids begins. And we have taken mixtures of different compositions. For each mixture, the freezing point or the freezing will commence at different temperature. Here it is at this position. Here it is at this position. Likewise, for different compositions, we'll obtain different freezing points. Can you understand why? Because it's a this. Hope you might be knowing this concept. When some impurity is added to a pure substance, it will lower the freezing point or it elevates the boiling point. It's a colligative property. Depression of freezing point is a colligative property. So when some impurity is added to a pure substance, it will lower or reduce the freezing point. That's why the pure substance will have the highest freezing point. When some impurity is added to 100%, when it's 100% A, the freezing point is obtained at this position. When it is 90% A and 10% B, freezing point is attained at this position. It's getting lowered. Can you understand? It's a colligative property. Okay. And notice the second break is obtained at the point at which this temperature is remaining constant. Can you interpret? Okay. Can you find anything similar in this? The freezing points, okay, freezing points are different for different compositions, but these points are the eutectic temperature will be the same for all mixtures irrespective of their composition. For this thing, it's this, okay, corresponding to this temperature. For this composition, it's corresponding to this temperature. For this one, it's, can you understand? So for any mixture, the eutectic temperature will be the same irrespective of their compositions. Okay, and for drawing this phase diagram, it's mandatory that we should know the freezing points of this pure substance, pure 100% A as well as 100% B. Okay, so the freezing points of pure A and pure B are also determined similarly. So how will be the freezing point of pure substance? So initial decrease, and when the solid begins to form, the rate of cooling, there will be a halt, and thereafter there will be a decrease. Okay, can you remember? So shape will be of this pattern. Okay, so that's what in this side and this side. This is for 100% A and this is for 100% B. Can you understand? Okay, and the cooling curves of a series of alloys of known composition are drawn like this, and the equilibrium diagram for the system of two metals. Okay, this is the equilibrium diagram of the phase diagram. Okay, for the system of two metals A and B is thus determined. Okay, so this is all about thermal analysis and cooling curves. Thank you.